Okay, in this screencast, we're going to look at we're going to start to look at the product of two vectors and what that might mean. We've looked at different operations on vectors, and we've looked at magnitude, and we've worked our way around different figures in 2 and 3D, and got our heads around vectors a little bit. Now we're going to look at the product of two vectors, which adds a little bit of complexity. It gives us much more information about how to use vectors to help us understand space and spatial measurements. So we're going to start. We're going to start by looking. Well, there are two different products. There's a scalar product and there's a vector product. Okay, so the two types of products that we're going to look at are scalar products, and that's what is we're going to look at today and probably on Thursday as well. And then we're going to look at the what's called the cross product, or the vector product. Slightly more complicated in that essentially the difference between the two is a scalar product results in a scalar. The vector product results in a vector. The scalar product is a measure of parallelness, or what it gives you a quantity that represents how far two vectors go in the same direction, and I'll show you in a moment with use of A and B here. Whereas the vector product gives you a measure of how far two vectors, or how they're related in a perpendicular sense. So scalar, this is a parallel relationship measure, if you like, or the strength of the relationship, a parallel relationship. And the vector product is a comment, or it's a comment, it's a measure, it's a report, it's an object that gives you a measure of the perpendicular relationship. So that's in a nutshell the difference between the two. So we'll now concentrate on the dot product, and so we'll just say here, firstly, we'll look at and we're most likely to talk about it in that sense. Now it's called the dot product simply because it uses a dot as its operator. So the dot product of two vectors has a dot between them. So the dot product of A and B will look like so. Now when you see it like this, perhaps when you see that might mean multiplication in another context, but when it's vectors and you see a dot between, it's talking about the dot product. So this is, you might talk about this as A dot B. So what it means is we're looking for the scalar product of A and B. Okay, let's go. Let's have a little look at how we get the dot product and what it actually means. So let's use these vectors on the screen. I've got a vector B here, which is so B is equal to 6, 0. 6 in the x direction, 0 in the y direction. I've given A is equal to 3, 3. I'm using intentionally quite specific vectors just to get the idea across. But obviously this will work for any pair of vectors. Okay, so of importance is, well, we'll come to that in a second. But what I'm going to do is we're going to find the dot product of A and B. Now, what that means is I need to find out how far they're both traveling in the same direction. So in order to calculate that, I'm going to project A onto B, and I'm going to see how much of A is traveling in the B direction. That's kind of how I think about it. So if I just now project A onto B, like so, little right angle here. So the dot product of A and B is going to be the length that A projects onto B. So this little length here, if I sort of highlight over it, this little length here, that length there multiplied by the length of B. So if you like, A dot B B is equal to this length here, which is the length that A projects onto B. So the length that A projects onto B, or you might think of that as the length that A travels in the B direction, and that will be multiplied by, and this is a length, multiplied by the length of B. The length of B. Now we've got a quick abbreviated way of saying the length of B. That's just B with the absolute value signs around it, but I'm just going through the whole process here. Now the length that A projects onto B, well, we can work this out because we have some right angle trigonometry up our sleeve, don't we? So I could write this here, and if I know this angle in here, that's going to be important to me. So if I know the angle between the two vectors, and in this case I do, because that angle is 45 degrees, I can see that I've got rise over run equal to 1. So my tan theta equals 1. I've got 45 degree angle there. Clearly it's not always going to be horizontal and etc., but we can always find this angle, and that might be a little more complex, but it's actually not that complex. So we can always get this angle. In this case, our angle is 45. So the projection that A is onto B in this case, we can work out by trigonometry. So this distance here, if we call it x, say, this projected distance, then cos theta, if we just peel off over here and work this out, cos theta is equal to my distance here, my A projected onto B, x over the length of A, or the magnitude of vector A. All right, so that's it there. So therefore, x is equal to the magnitude of A cos theta. Remember, x represents just this little highlighted distance here. So what we're saying is that the dot product is that length there. So I'm going to now write that as A cos theta multiplied by the length of B, which is just this. All right, and written in a neater way, we could write it as A B cos theta, and that is my dot product. Okay, well let's work out what that actually is for this example. Okay, so this length here, well, it's equal to the length of A. So in our example, maybe we'll just do that over here. So in this example, all right. So in this example, we're going to say that in this example, A dot B. All right, so we're just thinking about the product of these lengths. All right, so I'm just going to say, well, A dot B is equal to the magnitude of A times cos theta. So the magnitude of A is the square root of 18, 3 squared plus 3 squared, just the magnitude of that vector there. Cos theta, so cos theta is equal to cos 45, or it's just what's that? 3 over what am I saying here? Squared 3 over root 18. But we know what cos 45 is. It's equal to 1 over root 2. So we'll just multiply this guy by 1 over root 2. So that gives me my length here, my highlighted length. Now I'm going to multiply that by the magnitude of B, and because it's a horizontal line, that's not presenting us with too many difficulties. So there's my dot product. Okay, so let's figure this out. Root 18 times 1 over root 2. Well, that's root 18 over root 2, which is root 9, which is 3. So this is equal to 3 times 6, which equals 18. Okay, so this 18 is my scalar product of my vectors A and B, and it represents the distance that the combined vectors move in the direction of B. So it's their combined, I referred to before as parallelness. So if we just used our formula down here, A dot B, well, we're going to get the same thing. So we can think of this value of 18 as being the distance that vectors A and B move in the same direction. That's what we're doing. That's what we're getting. That's what it means, the interpretation. Okay, so here's our magic relationship between our vectors that give us our dot product. Right, this guy here, that's called our dot product. Okay, so having a look at another example. Actually, before we go on to another example, I should show you the quick way without using any trigonometry of finding our dot product. We can find our dot product, A dot B, by doing this. So for our example here, 3, 3, and 6, 0. Okay, so where A is equal to 3, 3, and vector B is equal to 6, 0, then we can find A dot B. A dot B will equal 3 times 6, multiplying our horizontal displacements together. So it's the sum of the product of the displacements plus 3 times 0, which gives us our 18. Now we worked out 18 out here before, so we've worked it out in two ways here. This was just going back to first principles, how far they move in the same direction. And over here we're just using a nice little trick, really. We get the same result. Now obviously this way is very quick, so that's going to be very useful for us to be able to make this calculation, but it's also very important that we understand what it represents. So now let's have a look at another example. Okay, another example here, vectors A and B in front of you. Now simply to find the dot product, all we need to do to the dot product is to multiply 4 by 7 and add 2 by 1. So we get 30. So all that does, that represents the direction of the combined direction of travel in one direction. So that would be if we projected A down here onto B, like so, then it would be this distance here that is that projection, that part of A that projects onto B, multiplied by the distance or the magnitude of vector B itself. That's what 30 represents. And the other way of looking at the dot product is, of course, to have a look at, well, what it represents is, it represents the magnitude of vector A by the magnitude of vector B by the cosine of the angle between the vectors. So this is also going to enable us to find the angle between vectors very quickly. We could find that angle. Sure, we could find it using trigonometry. We could find we could find it by taking tan inverse of we could find theta. We could find it by taking tan inverse of a half and subtracting tan inverse of 1/7, just using the angles made with the horizontal by both those vectors. This is going to get it for us very quickly. So the dot product's got is quite powerful in terms of what information it can it can deliver to us. So let's just now we'll just take down a couple of notes, summarize what we've done, and then we can do some examples, some questions from exercise 11J. Okay, so just a little summary here for vectors u and v, u being u1, u2, and v, v1, v2. The dot product u dot v is u1, v1 plus u2, v2. And what that does is it gives a scalar quantity that represents the combined magnitude of vectors a and b in the same direction, right? The same direction. So in summary, the dot product is a measure of parallelness, right? Whereas the vector product, when we get to it, will be a measure of perpendicularness. If I can make up some words. Okay, some properties. Right, let's just note some properties. Properties of the dot product. So we could say that well, u dot v. So there's they're commutative. They're very adaptable as it's just multiplication. U dot u is well, it's just the magnitude of u squared. There's a distributive property, so u dot v plus w will equal u dot v plus the dot of u and w. And in fact, we can scalar by a vector and then dot with another, and we can change the order of that. We can just scalar the dot of u and v. That's probably all. One more comment perhaps, and because the dot product is a measure of parallelness, if two vectors are perpendicular, if you can think about what that might mean, let's just wrap these properties up in a little container. But if we've got if we have perpendicular vectors, so well, there's two ways of looking at it. If we've got vectors a here and b here that are perpendicular, then the dot product a dot b will equal, well, there's no parallelness. There's no direction. We can't project b onto a at all. So b onto a gives a projection of 0. So that would indicate that perhaps our dot product has no quantity. There's no parallelness, so there's no quantity there. So it is true that if the dot product is 0, then we have perpendicular vectors. But we also would know that from the fact that this angle between the two vectors now is 90, and that right, I can take my values here, but I am now taking cos of pi on 2, and we all know that cos pi on 2 is equal to 0. So the dot product is equal to 0 for perpendicular vectors. Now, perpendicular vectors have a fancy name, and that is orthogonal. So so vectors A and B, if they're perpendicular, are orthogonal. So better just make that orthogonal vectors are perpendicular. So it's just a vector term for perpendicular vectors. And if the dot product equals 0, we say that if a dot b equals 0, then a and b are orthogonal. All right, let's just do one or two more examples, and then we'll move into the exercises. So let's have a look at, let's find a dot product for a 3D vector. So, all right, so let's say if u equals -1 to -3, -1 to -3, and v is equal to -4, -1, 2. Let's find u dot v. Okay, so in this case, good idea to pause, do, and then come back. So u dot v will be equal to -1 times -4, so 4, 2 times -1, -1, -3 times 2, -6. So I think here we had 4, we're down to 3, and now we're off to -3. So our dot product yeah, I spotted a little mistake here. That should be a -2 here. The product of 2 and -1. So 4 plus -2. We're at 2, add -6. So -4 is our dot product here. Let's do one more. Okay, so in this example, 3 points here, position vectors. Find AB dot BC. So the dot here between two vectors, dot product. So firstly, we need our vectors, so we need to establish what AB is. So AB will be equal to vector. So what are we doing here? We're going up 1, we're going up 1, and we're going down 4. So 1, 1, -4 for AB. BC, we're going from B to C, so up 1, 0, and up 3. So 1, 0, so 1, 0, 3. So therefore, my dot product AB BC will equal 1 plus 0 minus 12, which is -11. Okay, let's hit exercise 11J, and that's on page 589, and I think we can do all questions there.